Alrighty, so for this problem we are asked to find the magnitude of the couple moment. So I think it's really easy to see this problem and immediately just get very overwhelmed because it's asking about a couple moment and we have some thicknesses here and everything's coming in at an angle and what the heck is going on? And so let's just kind of slow down for a second and let's be strategic about what we need to do. So we know that a couple is produced when we have two equal and opposite forces that cause rotation. And so we have two equal and opposite forces, right? We have one here, we have this 6 kilonewton force, and then we also have this 6 kilonewton force. And we can see from the triangles that they're coming in at equal and opposite magnitudes, and they are also acting on the same ends of this beam here. So something that might be easy to do is let's be strategic about what point we find moments about. So what if we found moments about this point right here? What would that do? Well, since we're looking for moments, we just want to see how much rotation is happening, right? And so the tendency to rotate in not that direction due to this force right here, tendency to rotate in this direction, is going to be exactly the same as the tendency to rotate in this direction. And that should make intuitive sense because the forces are equal and opposite, and they want to spin this beam in this direction, like that. And so that means that the tendency for rotation from one of the forces should be exactly the same as the tendency for one of the other forces. And so then the next question becomes, okay, that's all well and good, but where do we actually take moments about to simplify this? Well, what if we did it around this red point right here, right? That would simplify some things because, well, we would have the moment in the x direction going there, passing through the point, so we wouldn't get a moment. And then we'd have the vertical direction going here, also passing through the point, so we also wouldn't get a moment. And so that means that we can essentially ignore the rotation that is caused this entire force about this point, right? And that's an important distinction to make because if we did it around this point here, then this force would cause rotation and this force would not. But let's get rid of that. Since we're talking about this force right here, there's no moment caused by this force, so we can just ignore it, pretend it doesn't exist. Okay, so now we're just focusing on this 6 kilonewton force here. So it's coming in at an angle, so we need to break it up. So let's call this F in the X and call this F in the Y. And we have a triangle, which we can see. Actually, no, let's make it green. So this side here is 5, and this side here is 4. This side is 3, so we can use that. Let's go over here, show the work. So we have a 5, 3, 4 triangle, or 3, 4, 5, however you want to say it. And we know that the magnitude, so the hypotenuse, is going to be 6, and then this is fx, and then this is fy. So now we just use proportions to figure out fx and fy. So let's actually move things over here so that you can still see that. And so we can let's start with, let's use this side, and then we'll use this side and this side. So that means that we have 5 over 3 is equal to 6 over fx. Multiply across, so we have 5 times fx times 6 times 3. So then that's going to give us 5x fx is equal to 18. And then that fx is equal to 18 over 5. Now let's do the same thing for Fy. So now let's still keep the 5 because we need to include the hypotenuse. So let's do 5 over 4 this time. Let's do 6 over 6 and Fy. Okay, so it means that 5 over 4 is equal to 6 over Fy. Multiplying across again, we can see that 5 Fy is equal to 24. And that means that Fy is equal to 24 over 5. Okay, I'm just going to underline these so it's easy for us to refer back to. Okay. Whoops, without moving that. Alrighty. Okay, so now that we have the forces, we need to look at the moment arms. And so I think the easiest one to see is we need to see the mutual perpendiculars. So I'm actually going to get rid of this so that we can see some other stuff. So the way that I like to do this is I actually sort of like to draw some dotted lines because that just helps me. And actually, since these are sliding vectors, we can actually move them wherever we want. And so I actually think that what we can do is another way we can just redraw this. We can draw fx as being here, fx being here, and then I'm going to move fy. And the reason why I'm moving it will make sense in just a second. And fy is here. Okay. So let's start with fx first. So I'm just going to draw a dotted line here. And so we have fx here, and remember that we're focusing on this point right down here. And so let's draw another line down here. So what is that perpendicular distance, right? We know that the perpendicular is going to be from here to this point. So here to here. So it's going to be, you cannot see that at all. Will yellow make it easier to see? Let's try yellow. It's going to be this distance here. So what is that distance? Well, we can just look. It's going to be the 1 meter, right, from here to here, right? Just given in the picture. And then we also have the 1 meter from here to here. So you add them up, 1 plus 1. Crazy that we're doing simple math like this in college, but that's going to be 2 meters. And now let's do the same thing for Fy. Okay, so let's draw our vertical line down, and then another vertical line around the point that we're taking moments around. Hopefully you can see that. You might not be able to, so I'm going to switch it to blue, and hopefully that will make it clear. Okay. So now what we want is this perpendicular distance here, which we can see is 5 meters. Okay, so now we have all the pieces necessary to start calculating moments. So we have a force, and we have a moment arm. We have the moment itself. And then we have the rotation. Okay. That I can't draw, obviously. Okay, so now let's start just tallying up our forces. So let's start with fx, right? And let's go back up here. You can see that that is 18 over 5. 18 over 5. And I'm going to split this. Let's go Fy is equal to, actually, you know what? I want to change that to 18 over 5. Let's make it red. And then this will be blue, which is 24 over 5. Okay, nice. So now we have, now let's look for our moment arm. So let's go back over to our picture. So we're looking for the moment arm with fx. So what that means is I'm looking for the mutual perpendicular between fx and the point that we're interested in. So that is, so here and here, which we found to be 2 meters. So let's go back and do that in yellow, 2 meters. Then let's do the same thing for fy. So we want here, and that is 5 meters. Do that in blue. It's going to be 5 meters. So in the moment, we just multiply the two. So for this one, we will get 18/5 times 2 meters. So it's going to be 18 times 2, which should be 36 over 5. And that is going to be Newton meters. And then this one, the 5s are going to cancel, so we'll just get 24 Newton meters. So now for the rotation, let's actually go and look at that. So let's start with fx. So this is actually why I drew the fx and fy where I did. I'm going to clean this up a little bit so there's less for us to look at, and it's just easier to see. Okay. Awesome. Okay, now let's just redraw some of this stuff. Whoops, not with an eraser. With a pen. There we go. Okay. This is fx. So I like to imagine, I actually personally prefer in my head what I do. See if I can take this and then can I move it? I actually imagine, and that did not work at all. I actually imagine fx, I'm just going to redraw the whole thing. So fy is here, so fx is here. What I like to imagine in my head is going on to figure out the rotation is I actually move it down so that I can actually see what the rotation would look like. So if we do that, we can see that that fx wants to push it this way, right? It wants to go like that. And so that is going to be counterclockwise. So rotation is going to be counterclockwise. Now let's do the same thing for fy. We don't really need to move fy, just because it's pointing straight down. And so if fy were to do that, we can see that it would want to rotate the beam this direction, right? So it'd be pushing down, and it would want to, around this point, it would go like that. Okay, hopefully you can see that. And so that is going to be, this is always the hardest part for me, this is going to be clockwise. Clockwise. Okay, so now we have everything filled in. So now we have the moment is equal to, and you can write it in vector form if you want, 36/5 in the, that's going to be in the x direction. Sorry, yes, 36/5, and then it's going to be 24 in the y direction. Now, to figure out the magnitude, we have to take into account the rotation. So by convention, counterclockwise is positive and clockwise is negative. So what we can do is we can subtract these two, and so we get 36 over 5 minus 24, which is equal to 36 over 5 minus, let's see, it should be 20, should be 120 over 5, which is equal to 120 minus 36, which I can't do in my head. 0, 11, it's going to be 4, 84. negative 84 fifths. And that is going to be our answer. That should be correct. Let me just double check that with Mathematica real quick. And that is indeed correct. The answer to this, I have it in decimal form, whoops, is 16.8. So that is, if you do the decimal, that is negative 16.8 roughly. And because we have that little negative hanging out here, that's going, by our convention, that means that it is going clockwise. So our final answer is that the magnitude of the couple moment is equal to 16.8. And technically this should be kilonewtons. I made a mistake. If you look over here, we are in kilonewtons. So, kilonewtons. Just gonna throw a bunch of K's in there. Is equal to 16.8 kilonewtons. Kilonewton meters. And we are done.